Yes, welcome everybody. My name is Luaga Michael, a member of CSC 241. Uh, on behalf of my colleagues, I'm going to be presenting this project called Real-Time Ugandan Sign Language Translation to Speech. This project involves translating Ugandan Sign Language to speech, where we input our videos in real time, or we capture our videos in real time using webcams on edge devices like phones, laptops, and we translate them to speech. These are the contents of the presentation, and I will go straight to the introduction. Being that we are using interfaces like laptops, phones, it's a human-computer interaction which involves capturing videos using webcam. It's also an assistive technology because we are helping the hard of hearing and the deaf community in Uganda to be able to communicate with the population. Our system leverages on hand tracking because we know as we are signing sign language, we use hand movement, also the pose estimation, because we move the body in different shapes. We are using computer vision because we shall be collecting these signs with with a webcam and translate them into images. And also we are leveraging on neural networks because we are capturing patterns from these videos. As you can see from down here, we are showing a person seated in front of a laptop trying to translate signs, and the output is audio. So some of the related works that have been done in the past, Jose et al. Created a large data set which inspired us to create our own video data set for Ugandan Sign Language. And also Park et al. Developed a sign language model with use of recurrent neural networks because these signs are time series, so that's why you use recurrent neural networks, which we also used in the transformer model. Lee et al. Also was successful to do transfer learning of the cross-domain knowledge of CNN for video sign language recognition. And also Kohler et al. Trained a CNN on hand gesture recognition. These people inspired our works because it is almost the same, but we are concentrating on Ugandan Sign Language. So the problem that we are solving, because we looked into the deaf and hard of hearing community, there is a problem of ineffective communication because they can't talk to people directly, and also which this hinders their full participation in aspects of the society and also utilizing their full potential. So we are looking at using a deep learning model whereby collecting a data set and also training it and developing it and training it and later deploy it. So that's the problem that we are solving. So some of the objectives here we have to develop a real-time sign language recognition and translation system that can accurately convert Ugandan sign language into speech. Also to collect and curate a video data set for Ugandan sign language. To build and evaluate a deep learning language model to translate Ugandan sign language, and also to develop an accessible lightweight user interface for this model. So those are the contributions that we made. We developed it. We constructed the video data set. We built and evaluated the deep learning, and also developed lightweight interface. This is the methodology, the pipeline, all the steps that we followed. We went and talked to the deaf and hard of hearing community. We collected videos. We cleaned the data. We did the exploratory data analysis in the video frames. We developed the model, we did accuracy testing, feedback, and real-time integration. So when you look at our data set, it is made of 106 word level videos that were collected from the Uganda Sign Language and recorded in a controlled environment. We did a controlled environment because we wanted to eliminate noise and disturbances in the background in order to extract our key points well. So this is the model architecture that we deployed, that we used. We collected our features, we extracted our features, and then we fed them to the attention mechanism, the transformer mechanism that was able to train and predict the text outcome. So in the process of training, we had three pipelines. We used media pipe, ResNet, and VGG19. But our main model was using media pipe. So here we are showing you how we are extracting key points. Remember, key points are extracted from the hand, from the joints in the hand, the two hands, face, and the paws. So that's why we are seeing the lines, dotted point joints movement. So we are extracting the position, the relative position of these points. They are the key features that we are going to feed into the model for every frame, and we shall be able to predict the word. So when we deploy, when we fed these features into the model, were high, the are high compared to the losses, which are also below, which are also low, meaning that our model was able to learn and perform well as expected. When we compare with other models that use the ResNet and VGG19, see that the model that the training accuracy and validation accuracy were but performed better than ResNet 50 because its accuracy is far above and its loss is also lower compared to the ResNet 50. These are the tabulated results of those. Remember, our model is translating video from sign language, from Uganda Sign Language to speech. But in the intermediate model, in the model that we have seen, we are translating video to text. Then the other module that we added on was to translate that predicted text into audio. And when we were translating this, these are live spectrograms of audio recordings that we got. Or if, as you can see it there, it is just the spectrogram that we are able to print out, and other predicted texts, we are able to translate them well. Then in the conclusions here, we are seeing that the multi-head attention mechanism helped us to focus. It helped us to focus on different parts of the input sequences simultaneously, which was able to capture complex dependencies and enhancing the understanding of interact or the complex sign language gestures. And that's why our models were able to perform better. Then in the limitations, what we got was the complex sign language because of the different contexts and the note, and also the data collections phase are why we are able to collect, because we collected only 106 because it was expensive to have these people sign for us. We needed some money, which we didn't have. Then the computational resources, these are neural networks that deploy GPUs, that use GPUs and memory, and we look at these constraints because our machine that we used was slightly below the required standards. In the future works, we are looking at expanding these datasets, doing model enhancements and collaborative efforts. We want to acknowledge Mr. Gariwango, who has been our supervisor in this project, who has done us good work, immeasurable, has given us his time and knowledge. So we want to thank Yusuf Senyomo of UBC, who gave us who allowed us to record him for our data set. These are our references. Thank you for listening. Have a good time.